Graphing Quadratics Part 2. This video will cover standard form. So I'm going to write down what standard form is. Where A, B, and C remain some constant value. So what we discussed in Part 1 was what we called vertex form. So let's reintroduce that, and it looks something like this. Now, if we were to expand out vertex form, we're going to see a relationship between vertex form, expanded version, and this new standard form that we just introduced. If I carry out x minus h squared, remember that's x minus h times x minus h, and through that double distribution we'll get x squared minus 2xh plus h squared plus k. Distributing the a to all the terms, we get ax squared minus 2ahx plus ah squared plus k. Now, let's draw some parallels between the standard form that we wrote above and this new expanded version of the vertex form. We'll see that a in front of x squared still remains unchanged. So a in the standard form still equals a. The b equals what's in front of the linear term x. What is in front of the linear term x but this minus 2ah? So we're going to write minus 2ah. That's what our b corresponds to in our standard form. And then lastly, our c corresponds to that ah squared plus k. So we can say c all right, so if A, B, and C in standard form corresponds to each of these pieces from an expanded out vertex form, what can we learn about what A, B, and C tell us in our vertex form? Well, first off, A in the vertex form revealed vertical dilations. It told us if the graph opened up or down depending on if a reflection was present. And because A in the standard form is the same as A in the vertex form, that means it should reveal the same information. So A in standard form tells us still vertical dilations. It tells us whether or not the parabola opens up or down, so we can think of that as direction or vertical reflections. Okay. So A still means the same thing. Now, what does B mean in our standard form? Well, B is negative 2AH. So, if you recall from the vertex form, we can identify the location of the vertex pretty easily. And in the case of the vertex form that we have, the standard form, the vertex is going to be located at HK. Okay, if we go right H, up K, that puts us at HK, which means the axis of symmetry is at H. So if H is the axis of symmetry, then we can manipulate this equation where B equals negative 2AH by solving for H. And what happens through there is that we'll get H equals negative B over 2A. So if H represents the axis of symmetry from our vertex form, then we now have an equation that allows us to find the axis of symmetry from the vertex form. This equation here will tell us the axis of symmetry when we're in vertex form. I identify A and B and utilize that equation. Now, if I know the axis of symmetry, then I can get the vertex, because I know that the x-coordinate for the vertex is the same as the value of the axis of symmetry. So negative b over 2a is going to be my x-coordinate for my vertex, and to find the y-coordinate, I evaluate the function at negative b over 2a. So this here gives us our vertex. So a lot just happened there. We were able to define b by drawing a parallel from the standard form to the expanded vertex form. We found out that b is negative 2ah. And what we know about h from the vertex form is that it represents the axis of symmetry. So solving for h will reveal a formula that allows me to calculate the axis of symmetry given standard form. And if I know the axis of symmetry and its relationship with the vertex, I know that I can find the x-coordinate of the vertex because it's the same as the axis of symmetry value. And through function evaluation, I can find the corresponding y-coordinate. So a lot there, a lot of information embedded within that little piece that we initially discovered. Now lastly, C, AH squared plus K. What's going on there? Well, if you look at the vertex form, what looks similar here? Well, if x were 0, won't I get AH squared plus K? And what's special about when x equals 0? Well, when I'm on a coordinate plane, anytime x is equal to 0, I've just discovered a y-intercept. All points along the y-axis, no matter where I place this point, they all have an x-coordinate of 0. So no matter where I am, I have an x-coordinate of 0, which means that if this c being equal to AH squared plus K is a result of x equaling 0, and I know that when x equals 0, I have a point on the y-axis, that means the c value is telling me the y-intercept of my quadratic equation when in standard form. So the y-intercept is equal to whatever c is in my standard form. So interesting result there. And as a side note, this is for all functions. To find a y-intercept, you evaluate the function when x equals 0, because all y-intercepts, or all points along the y-axis, have x-coordinates equal to 0. So if you plug in 0 for x, that will reveal to you the value of the y-intercept. So interesting result there. So let's generalize some interesting aspects that we can discover through standard form equations. First thing, we can identify the direction, meaning does it open up or down? It will open up if the a value is greater than 0. And what do I mean by opening up? It looks something like that. So if a is greater than 0, no vertical reflection has occurred, and we know the standard or the parent function for the quadratic opens up as is, that x squared. So if no vertical reflections occur, it should still open up. It's going to open down, however, if the vertical reflection occurs, and that will occur if we make a negative, because that would be multiplying by -1. So that's the first thing we can identify, is direction. Does it open up or down? And that is all dependent on the value of a. And again, this is when we're in standard form. The second thing we can identify is the axis of symmetry. And that will be found by computing or evaluating x equals negative b over 2a. And we saw where that came from up above. 3, if I know the axis of symmetry, I will be able to get the vertex. And we said the vertex and the axis of symmetry are related in the sense that the value of the axis of symmetry is the same as the x-coordinate in my vertex. So whatever that value was, we carry over to the x-coordinate, We evaluate the function at that point to get the corresponding y-coordinate. So this is our vertex. Next, if we can figure out if it opens up or down, and we can identify the location of the vertex, then we will be able to identify the maximum or minimum values or slash locations for our parabola. So if it opens down, then you have a max. You have a highest point. If it opens up, you have a minimum or a lowest point. Now, given the nature of the parabola, the max and min point, that point is the vertex. Okay, so you have to decide, does that vertex represent a maximum or minimum? And that all depends on whether or not it opens up or down. Now, the vertex is going to be at some location, some xy coordinate, as we discussed before. That coordinate itself reveals some information within it. The x-coordinate of the vertex tells you where the max or min occurs. The y value of that coordinate tells you what the max or min is. This is important when we look at applications of quadratics. Where or when does the max or min occur? So let's add in when, in case we have a time application. And then what the max or min value is going to be whatever the y-coordinate of that vertex is. So again, that comes into play with application, so it's important to know what information is embedded within that coordinate. Next, we can identify the y-intercept. We said the y-intercept is the value of c in my standard equation. And again, if you ever forget, just know you can always find the x-intercept by plugging in 0 for x. So y-intercepts, when it comes to application stuff, this often represents an initial amount. So when x is 0, before anything has happened, that initial amount. So when we do application problems, know that the y-intercept represents that. So those are the pieces that we can find just by looking at a standard form equation and identifying A, B, and C. You'll notice that all of these things are dependent on your identification of the values of A, B, and C within their standard form. So that is the second form that you are responsible for knowing.